All right. Okay, let's get started. Okay, here's the road sheet for today. I'm just going to pass it around. All right, we have a lot of stuff to do today, so let's go ahead and get started. Okay, I'm not going to wait for people who come in late, because we just have too much stuff to cover today. First of all, the homework assignment read base 16 is basically due as of about 2 minutes and a half ago. So we'll go over that and talk about the solution to that homework. But let me just open up the new project first, just so that you guys know what is the next project we work on. And I think sometimes, okay, I'll do this in a way to make it work. Okay, there we go. So this is our new homework assignment. It is called Subroutine number 1, which means, from now on, every single homework assignment is going to be related to, guess what? Subroutines, functions, subs, whatever you want to call that. Okay. So what we want to do is to implement these particular subroutines, okay? One is called put char, something that we have seen already. This one is a little bit different because, well, I guess it is the same as the other one. Oh my goodness, I just gave you the solution in my previous class. I won't tell you which part now. Okay, so you guys have to watch the video and find out which part you can just copy and make it work. Okay, that's okay. Calm down. Okay, I'm good. All right. Okay, the second function, which is function f, is something that you have to do. This is written all in C. In other words, you can plug it into a C program and actually how it works, okay, which is recommended. If you look at subroutine F, you can do it in Visual Basic if you want to. You don't have to do this one in C because the logic contained in this subroutine is relatively simple. And you can do it just in just about any programming language. I'll just take a look at this line by line. You have two parameters. One is x and one is b. They're both passed as unsigned integers. They are 32-bit integers. If x is less than b, then you go ahead and print out the character corresponding to x. But you have to remember to add the ASCII code of 0 first, because otherwise you'll be printing a control character instead of a character that you can actually see on the screen. Because if x is 0, 0 plus the ASCII code of 0 is what? The ASCII code of 0. When you print the ASCII code of 0, the 0 appears on the screen or it is stored in a file. So that's why we have to add the ASCII code of 0 to x, in order to print it out in a way that we can see it. If that is not the case, then we have a little recursion going on here. Okay, and the recursion is we will pass the quotient of x divided by b to parameter x, and b is going to be passed along just by itself. And then after we return from the recursion, we'll do the second part, which is taking the mod of x mod b, taking the result of x mod b, and then just add the ASCII code of 0 to it. Now, obviously, in this case, b has to be up to base 10. I can only specify everything from 2 up to 10 for b, which is the base. And this subroutine is just printing the value x in base b. That's all that it does. So I can print something in base 5, in base 7, base 9, base 8, whatever I want to use. Okay. Are there any questions? Yep.
Are you going to help us try to write modulus and assembly code?
Oh, yes, absolutely. I give you everything that you need.
Because div might be possible, but modulus is crazy.
Oh, it's easy. It's easy, sneezy. We'll get to that part. Okay, the assembly code to test your C code, which is basically a stub main. Now, in assembly programming, at least at this point, we don't have the concept of a main function. So I will just give you the code of the assembly code that you will need in order to test those two functions. Yes? Yes, we're passing by value, and we'll talk about that today. Yeah. And then here are the instructions. Folders and file names. This part you can pretty much read by yourself, but I'll just go ahead and read it anyway. You have to create a folder called print base. The case is sensitive, okay? Make sure you use lowercase p and uppercase b, and so on and so forth. The part that is kind of interesting is each C function will need its own file named after the function name itself. And this is because every function or different functions within the same source file will actually share labels. So that makes it easy to make mistakes. If you have any conditional statements, and you have these labels, you can actually end up with one subroutine's jump going into a label of another subroutine. So from now on, we implement one function per file. Every function, every subroutine has its own file, which is just more of from the organization perspective. It really doesn't change the logic of the program. It's just from the organization point of view, it is easier. It also makes it easier to compute the offset to parameters, and later on we'll also talk about local variables. So this is a good way to organize everything so there's no contamination between subroutines. So in this case, yes?
So you said it is going to print out, so it's pretty much right out?
Sorry? It will print, the code will print out a number in base B, whatever B is. So I will only specify B to be from 2 up to 10, because anything after 10 is not going to print out as a digit. It will just use the ASCII code of whatever is after 9, which I don't think is alphabet. Okay.
As in on the screen, like.
Okay, let me just finish reading this part here. It actually contains everything that you need. So in this case, you will have to create 2 additional files. One is called f.s, and the other one is put_char.s, which are named after the subroutines that you're supposed to implement. I suggest in italic that you use a makefile to help manage everything, because without a makefile, somebody is going to forget to reassemble a file, relink to the executable, and then the program does not behave the way it's supposed to. Okay, so a makefile will make sure that that is all done. But we haven't talked about makefiles yet, and that's something that we'll talk about later. And that part is up to you. If some people prefer to take it the painful way, don't use a makefile. It will make your life a whole lot more painful. Trust me, it will. Given what I have seen so far, in other words, in the lab, looking at how people work on the programs, I also strongly recommend the use of a revision control program such as RCS or GET. Okay, you can use CVS. There's a whole ton of revision control programs that you can use. Some of these are very easy to use, like GET is very flexible, and yet it is also very easy to use. You can find online tutorials and stuff like that. It is recommended, but it is not required. Okay, so here's the assembling part and linking. Use this command to assemble a file. And for some reason, the space doesn't show up here, but that's okay. Later on, I'll give you like a really good. You should know this part already. Okay, this is the part that you should know already. The only part that we haven't really dealt with is how do you link when you have multiple object files. This is how you do it. You use LD-O and then the name of the executable, and then after that you have to supply the .os of every single object file. The object files are created by the assembler, the AS command. Then you use GDB print base to debug the executables. Restrictions, you do have to implement the function calls and parameter passing on the stack as we talked about in the class. In other words, you cannot just say, oh, this is a fairly simple program, I'll just go ahead and use registers to pass parameters. You have to use the stack to pass registers as we talk about it today in the class. You must work on this assignment manually and independently. If I think a program is not written manually, and I can tell, there will be no points rewarded. This only applies to people who know what I'm saying. Christ. Not that I think you'll actually do it, What I'm afraid of, you tell somebody how to do it, and that somebody is actually going to do it this way and turn it in. That's what I'm afraid of. So you must implement the logic of the subroutine F as described in the C code. In other words, you look at this code here, and you say, oh, I can do this without using recursion. You cannot do it. You have to use recursion. Now, is recursion any more difficult than a regular subroutine?
No.
No. It's the same thing. It really is the same thing. So this is what we'll do is we'll use recursion in this program. Okay, now here answer to your question about how to divide and how to do the mod. Click here for a secondary source of information, but we don't really have to do that. If you want to do that, that's fine. Before the instruction to perform the division, make sure EAX has bit 0 to 31 of the dividend, and EDX has bit 32 to bit 63 of dividend. In other words, the dividend is actually a 64-bit dividend. The divisor, on the other hand, is a 32-bit divisor, and you can use another register to store the divisor. After the division instruction, which takes one single operand, which is the divisor register, the quotient is stored in EAX, and the remainder of the division, which is the result that you need for mod, is stored in EDX.
That's really simple.
Yes, one thing does both of the things that you want to do. For example, if you store the divisor in EBX, the instruction is going to be like this. You just have to make sure that EDX and EAX are properly initialized before the instruction. That's basically the key to use the divide L instruction, divide long. This instruction will modify all the status flags that we discussed in this class, so the Z, C, O, and S flag will all be changed. Yes?
How do the status flags relate to the division operation?
They mean exactly the same thing. Well, the quotient is what it uses to determine the zero. Okay, so that answers that question. How will my script test your program? My script will put a breakpoint right here before the call. So by that time, the two operands should be set up already. So what my script is going to do is to change the content on the stack to the test values, and then I'll just continue the execution of the program to function f. And the function f is supposed to write something to the standard output file. So my script will redirect the output to an actual file, and then I'll compare the file to what it is supposed to be, and that's how I will test this program. Okay. Are there any questions about everything that I have talked about so far? Yep.
So your assembly code to test for us to test with, that looks to give only 2 static values. Should we change that a little bit?
You should change it. You should change it to kind of like tricky test cases, like printing out 0, okay, a value of 0. You might want to try, base 2, all the way up to base 10. Yep.
And also, should we sanitize the input at all, or just assume it's going to be okay?
The input is just, these two operands. There's no standard in as input.
Well, no, I mean, like, should we make sure that B isn't 0 or something?
No, I always, pass you, reasonable values. So you don't have to check for, invalid values. Yep. Okay, so moving on. How do I find out what function f is supposed to do? If you took cisp310 from me, you can trace it by hand. Should be able to. Okay, otherwise you have to retake cisp300. If you did not take cisp300 from me, then what you can do is you can just write it. I mean, it's a C subroutine. You can just write it, fix all the syntax errors that I might have in that code, and just run it. Okay, and I suggest that you run it through a debugger, so you can run it step by step, line by line, and then figure out what the code is supposed to do. Yep.
So we didn't have cisp310. We didn't take that. We're supposed to do what again?
If you did not take cisp300 from me, then you write a simple C program and test it as a C program. Or Java, or Visual Basic, or Perl, PHP, Python, Lisp, Scheme.
Assembly.
Yeah, that might be a little bit more difficult. Okay. So are we doing okay so far with this? Okay. How do I implement the right function? Read my notes, because we have done it already. And this is actually system surface number 4. And remember what I said at the very beginning? I actually did it already. Okay, so I sort of did it already. So you just have to read the later part here to realize that I did not actually do everything that you can turn in for this assignment. You still have to do a little bit more work. It's not a whole lot more. How do I compute the address of CH? Read my notes. Surprise, which is this little icon here. For some reason, it doesn't show up as an emoticon. It shows up as a word. And combine some of the concepts. So we'll talk about that today, too. Do I have to use the frame pointer? And the answer is yes, because that's the whole point of this homework assignment, is for you guys to realize how to use the frame pointer so that you can refer to parameters that are passed on the stack. I don't have enough registers because you only have 4 or 8. You can push it, but you won't have enough registers to do everything. You can use push and pop to save and restore the registers. When you do that, you make sure that you watch the order of the push and the pop. What you push first will be the last thing that you pop. Otherwise, it will pop into the wrong It will pop into the wrong register. Throw me a bone here. Okay, here is a bone. Okay, so I'll just show you what the bone is.
Is it a file with just 3 folders in it?
Exactly. It's a folder with all the stub functions. One is already done. Print base is already done. It's basically the same code that I talked about in the description itself.
Can you give us the make file too?
I also give you the make file.
Then I will have to
So all you have to do is to say make and then GDV it. And I can just briefly explain what the make file is. I should have made this a little bit more readable, but I did not. This is what we call a target. Whatever is to the left-hand side of the colon on a line that does not start with a tab is a target. This is the target, which is the result that we want. The target will have a dependency, which means these are the files that it needs in order to create the target. And the line next to it, which is starting with a tab character, this is the command that you use in order to start with the dependency and end up with the target. And we just have 4 rules in this case. The first rule, okay, the most basic rules are these guys. We basically say, okay, I have an assembly source file. I want to create an object file. How do I do it? You use the assembler to do it. These things are just shorthands. $@ is the target, and $caret is the dependency.
Oh, that's really cool.
And it is really cool. I should have used the $@ here. I just forgot to change the first one to also use the target variable. But this works, okay? So even if you don't know what it means, it still works. Let me show you, just quickly, how this works. So I take this guy, extract it to. Well, I can extract it to today's folder, so you can refer to that later on today.
Oh, that's really cool.
Extract. And go to a command prompt. Today is 2011-0331.
Excuse me.
Yes.
So how many files are we supposed to have for the homework assignment?
How many
different files?
Different files?
Yeah.
This is it. These are the files that you need. You basically, I give you all the stub files already, okay? And what you need to do is to write the actual code in f.s and put charge.s. That's you need to put some code into those. I can show you every single file, what they are, what they look like. This is in f.s. F.s is just a stub function. I am even kind enough to remember to give you the return instruction, just in case some people will forget to write the instruction of the return. And this is another reason why we want to have one subroutine per file, is so that we can easily check that the subroutine has a return at the very end. If you write multiple subroutines in the same file, sometimes if you forget to write a return at the end of one, it will just kind of fall through and start to execute whatever subroutine is next to it. So this is yet another reason why we want to do it this way. Yep.
Can you explain the similarities between like the files that we have in C++, like the header files and like implementations?
There's no header file at this point.
So how do you connect those files together?
You tar the whole thing in the end.
No. Okay.
The linker.
The linker will do it.
So which one is the base one, like the main one?
That'd be print based.
Well, there's no such thing as main because we don't have the symbol main. But the underscore start symbol is defined in printbase.s. So that would be your entry point. That defines the entry point. This is the make file itself. I don't think you need to change the make file. So unless you want to, make it better or do something like that, don't change it. Okay. This is printbase.s. I don't think you need to change this file either. Okay. This is the entry point of the entire program. All it does is to set up the stack and perform the function call and then clean up the stack and exit the program appropriately. So I don't think you need to change this program either. And your job, your main job, is not this one, because as I said, this one I have a pretty close to final solution already. You just have to make some minor changes to use the frame pointer instead of the stack pointer to compute the address of CH. We'll talk about that today. And yes, that's it. So when you have this entire thing unzipped into your own folder, you just say make. That's it. It might complain about the clock skew, so what you can do if you see this message is to touch all the source files like this. It will refresh the timestamp of all the source files, and then if you make again, it still complains. Okay, maybe it's the make file
like
itself.
being touched.
Yeah. Depends on how you do it. There you go. The make file itself is the problem. Okay, so every time after you make changes to any of the .s file, you just type make again, and then it will bring the target up to date. Yes.
Am I reading that warning correctly? The make file was made a couple thousand seconds in the future.
Yeah, I think it has to do with the time base. It depends on how you run your virtual machine, and in this case, this is the wrong time because it has to do with this machine usually has Windows, and in Windows, it stores the local time. In Linux, it stores UTC, and then you have to tell the operating system your time zone so it can do the conversion, and that's why it is way off. When you do it on your own virtual machine, I think it would be right.
That time's wrong.
Scoring the microphone, that's right.
I thought was
It is right for a different time zone. How about that? we are not in. No, this is it's the correct time for this time zone, but this is the UTC time zone. Yeah. Yep.
So, what is it comparing against to get the idea that it's a couple thousand seconds off?
It's the difference between our time zone and UTC, basically.
Well, yeah, no, but what is make comparing the times against to get it off?
I think make is looking at make file itself. Let's take a look at all of these. I changed it already, so it's not going to do that anymore. There's no time skew anymore. Because all of these were touched today, or right a few minutes ago.
So it's comparing to the previous time you booted?
I think so. Yeah. Now this is what you need to do. When you change a file, okay, I'll just add a comment here. Okay, this is Subroutine F, okay, which doesn't change the code itself. All you have to do is to say make. You don't even have to say what you're making because the default target is the first target, and that's the executable. So when you say make, it will do whatever is necessary, the minimum necessary work to assemble and then relink to bring the target up to date, which is great because now you can make changes to 1, 2, or 3 files. Just type make, and then you can GDB, and you know that the target is going to be up to date. It's going to be correct. So are we doing okay so far with the tools that we need for this particular assignment? Yep.
So is there a maximum of how many files you could link up?
I don't think there is any practical, theoretical limit. I mean, obviously there is a practical limit at some point, but I don't think we're even close to running against that limit. Are we doing okay so far with the homework assignment? How it is all set up? Yep.
For the function file, like after the function, right? Do we have to make dot test?
Do you have to make
dot test?
dot text?
Yeah, do you have to?
It's not reading from a file. We pushed up.
It's
on
not
the
reading
file.
from a file anymore, so you don't have to. Basically, what you want to do is to change the stack content at the label, and you can test it that way. If you want to, the shortcut is to change print base.s. You can do that too, but that means every time you want to test with a different value, you have to change that source file, which is okay with me. It's just more troublesome that way.
Just make an X, make a Y, and then set those, push those.
You can do that too. You can also directly change the content on the stack using the set command.
Oh, really?
Yeah, you can just set a certain memory location to a certain value. You can look up how to do that in GDB, because that's what my script is going to do. Is to change the stack content directly. I think you can do an asterisk $ESP to dereference the stack pointer. Then you can change that location to whatever value you want it to. All right. So any questions about the homework assignment? We'll go over the concepts today. Is that good so far? Kind of? No?
Yes.
Okay.
How long do we have? A week still?
2 weeks?
How long is this homework?
Make it 2 week?
Okay.
Then that means the homework assignment after 2 weeks is going to be super duper extra difficult.
Oh, we can make this one too.
This
Still
one
get
is
another
not
one next
that
week.
difficult. Trust me, it's not that difficult. I mean, you think about, okay, why do you think this is difficult? Because I made it?
You gotta be organized.
Because I mean, look at this list of instructions. I mean, come on.
Well, but the instruction law means it's good because that means, it makes the job easier because I'm telling you how to do it already.
We're trying to scare people.
I don't think anyone should be scared, because if you look at this code, it's shorter than the previous program. It is shorter than read, base 16.
Yes, but talking about assembly, we can't trust you, Jack.
You cannot trust me. That's right. That is right. Okay, let me just talk about the concept first, because once you understand the concepts that you need in order to do this homework assignment, it really is not that difficult. We are now up to call frames. Actually, we are a little bit after call frame. We are starting on parameters, local variables, and the return value, of which we only need one thing for this assignment. For this assignment, the only thing we need are parameters. Okay, so we don't even need local variables. We don't even need to know how to do return values. The only thing we need are parameters. Okay. So the first thing we need to talk about is how to push the arguments on the stack. Now, how many people actually had a chance to read this after Tuesday? Okay, very good. A few. Okay. It's really important to do that part, because this class depends on people actually reading the material first, so that we can, when we talk about it in the class, the concepts will sink in more effectively. Okay. Many functions require more than one parameters. Okay, let me just go up one level here. Let's start with the first slide. Parameters are set up by the caller of a subroutine. We have done that already. Okay, we did that on Tuesday, and I illustrated the whole thing using what? A spreadsheet. The spreadsheet. Okay, remember the spreadsheet? That's going to be very, very important. When we talk about how to use the stack and parameters and local variables. And so what we'll do is we'll start to push. We'll talk about how to push arguments on the stack so you can pass arguments to a subroutine. The first thing I want to do is to show you this code here. Sum of integers. Okay, it's just going to add up a whole bunch of integers and then return the value or the sum of all those integers. Has anyone seen code like this before, or this is new to most of you? New? This is C code. This is regular C code, which you can also do in C++. There's nothing really important here except for the ... The ... are not exactly just, it's real. Okay, you can actually write this program and the compiler will take it and it will interpret the ... as I don't know how many more arguments will follow. Okay, so this is a subroutine that will take a variable number of arguments, but it has one as a minimum. In other words, first is a required parameter, but you can supply any number of parameters after that. Okay, but when you look at the source code, it explains exactly how it works. I have a local variable called sum here, and I will just initialize it to the value of the first integer. Okay, that's the first item, that I see. But how do I know where the rest of where are the rest of the numbers? Well, I have my local variable pnum, which is a pointer to a number, and I have it initialized to the address of the first argument. Is that doing okay so far? Okay. And I will say, as long as whatever pnum points to is non-zero, I will do the following. Okay. In other words, if I give, when I call this subroutine, I have to end the entire sequence with a 0. A 0 is basically a terminator and say that there are no more numbers after this. That's how I can tell when to stop. per iteration, this is what it will do. It will do a post increment on pnum, and then it will do a dereference. In other words, it's expecting all the other arguments to be, in terms of physical memory, to be on top of each other. Yep.
Wouldn't this add first to itself before incrementing pnum? You're basically
That is correct. You're adding the first number twice.
Oh,
So the code is incorrect, from that perspective. Yep. And then it will just return sum. Okay. And the explanation is like this. And this is a demonstration of how to actually perform the call. You can call some ints and just give it a whole bunch of numbers, but you do have to make sure the last number is a 0, because otherwise the loop will just go crazy, and it won't stop until it sees a 32-bit integer that is 0.
Yeah, which could be anywhere.
Which can be anywhere, exactly. Yep.
So you can't pass it 0 because it'll just stop.
Yeah.
If you pass it 0,
Like as to use as a
it will
parameter.
stop. It will stop because I should have changed this to a 0 here. If I initialize sum to be 0, then the whole program will work correctly, because whatever pnum points to will be 0 to begin with if the first number is 0 already.
No, I mean, what if you want to pass it 0 as a parameter? It won't take it. It'll just use that as a stop.
It can only be the last number. Yeah, 0 can be passed, but it can only be the last number, because it won't process anything past a 0. You can pass it anything you want, but it won't stop. It will process up to the first 0, and everything after that it won't add. Yep.
Why not do something smart and make the first argument the,
The
number
number?
of
You can do
parameters
that.
to pass it, and then
Well, the whole point is to illustrate that you can do something like this. Okay. So.
we can always use poor design. That's never a question.
Okay. Yeah, but in this case, that's not the whole point. The whole point is this part here. Now, the whole point is, how do we do this call? In other words, this function call here, just this part, how is it done in assembly? How am I going to pass a number of parameters like this? And the answer is, we do it like this. We push the parameters, but the order is reversed. In other words, the last parameter is pushed first. Okay. Now, after you understand, what the push instruction does, or what we actually do when we have a push instruction, which parameter would have the highest address here? The 0. Okay. So that means the code in C is going to work out, because 0 is basically the last item in the quote-unquote array. It's not really an array, but we can locate it as an array. Okay. So are we doing okay so far with this example here? This slide is here because a lot of times people will ask, why are we pushing the last parameter first? This is why. Okay? Everything that we do in this class is consistent with the C compiler. And this is exactly what the C compiler will do, is to push the last parameter first, and the subroutine knows that the caller will do exactly that, and therefore they can still they can communicate. It knows where to find the parameters. So is that okay so far? Okay, you kind of have to combine this with what we talked about on Tuesday, because those two, this class and the class on Tuesday are closely related. Yep.
So if the program, or if the function sumInts is using those numbers, why do we then have to subtract 4 times 7 when we're done?
Because the stack is not cleaned up. I have to clean up the stack. If I have 7 push instructions here, it's going to consume 28 bytes on the stack. If I don't do this part here, the stack pointer will still be off, which means I'll be wasting space on the stack when I don't need that space wasted like this.
Oh, sumInts is still storing them on the stack.
There's
Yes,
no pop
Okay.
there's no pop instruction. The subroutine does not pop. The
Okay.
subroutine just says, the subroutine says, I'm expecting the parameters to be there on the stack already, so it knows where to find the parameters. But when the subroutine is all done, it will just execute the return statement or the return instruction, but it will never clean up the stack. And that's why the
Okay.
caller is responsible to clean up the stack as well. Whoever sets up the parameters is responsible to clean up the parameters.
Okay. And where in our assembly code are we storing the return value?
The return value,
Yeah.
the call instruction will automatically save the return address before it passes control to some ints.
Okay.
So now we move on to the old and the new frame pointer. It is also a convention that the subroutine will push a copy of the frame pointer, which is EBP in this class. So from now on, just remember, when I say frame pointer, it is the same as EBP. EBP stands for enhanced, B is base, and then P is pointer. So this is what we call a base pointer. But in this class, we call it a frame pointer. In other words, almost every subroutine will start with this particular instruction, and immediately after this instruction, the frame pointer is overwritten to begin as a reference point of the current invocation. In other words, we will take a snapshot of the stack pointer so that it becomes the frame pointer. Are we doing okay so far? No? The first two instructions of a subroutine is going to be like this. Okay. So every time we use the frame pointer, you have to do you have to push the frame pointer first, and then you take a snapshot of the stack pointer, so that the stack pointer at that time becomes the frame pointer. Yes.
Two questions. One, is that what -m omit frame pointer is about?
Possibly.
And two, why?
Why what?
Are we copying the stack pointer to the frame pointer?
So that we can use the frame pointer as a reference point to address everything that we need, including the parameters as well as the local variables. Okay, let's go back to the notes on Tuesday, because that's going to be helpful in this case. So this is the Tuesday files. And what I'll do is I will, or is it stack trace? So what we'll do is I'm going to change this program just a little bit to reflect what these additional instructions will do. This is the file that we were working on Tuesday. I will save it in today's folder, so now it becomes a new file. Now we can start to make changes to it without losing what we had already on the other day. Okay, so what we are talking about is if we insert two more instructions here. Insert row, that. And what we're doing with these two new instructions is the first one is push L, or just push, the L is implied, and EBP. We are saving the value of EBP before we move the stack pointer to the EBP. This is what we are doing from now on with all our programs. Okay, so the question is, what is that exactly doing, and why do we want to do that? This is what we'll do next. Somehow the indentation doesn't work out correctly. I think the other ones are spaces. Let's take a look at the trace and see how this is going to change the trace itself. So we are now looking at line 5. Okay, we'll just go ahead and, I'll go ahead and erase everything here. Delete all formats. Okay, so we'll delete everything here. Going from line 3, we'll go to line 5. Okay, what does line 5 do? Does it do anything on the stack?
Yes.
Okay, what does it do on the stack? Pushes the frame pointer. Very good. So we'll go ahead and take the next 4 columns and say this is our old frame pointer, old EBP. And our stack pointer will now be adjusted, right? Every time you push or pop, the stack pointer gets changed. So in this case, it will get changed as well. Format cells, go to folders. Are we doing okay so far? And the stack pointer obviously is going to get adjusted by 4, so now it is L1 minus 10. Are we doing okay so far? Okay. And what do we do on line 6? Does it change the content on the stack? What does it do? It makes a new reference point, doesn't it? Okay. So that means, we are taking a snapshot of the stack pointer to become the frame pointer. So the frame pointer will point to exactly the same place. In other words, I'm not sure how I want to do this, because later on I might need to change the format here. I'll just go ahead and do it this way. So that means at this point, I'm not sure. This is a little bit difficult for me to do because I don't know exactly how far it will go. I'll just go down all the way down to I'm trying to figure out how to do this exactly. Okay, this is what I'll do. I'm going to use a different color, say red, to represent the EBP. And I'll use a thicker line too, just like this. Okay? I'm not sure, can you guys see the different colors?
Vaguely.
Very slightly.
Very slightly? Okay, well.
Yellow.
Oh, yellow.
Green.
You don't see it all.
Oh, light green, that would do it.
Oh, there you go.
Beautiful.
Yeah, cool. Okay, so now we have two registers pointing to exactly the same place. Okay, so it doesn't sound like it's useful for anything. Well, let's keep going. Okay, so this is line 6. Yep.
So what register is that? ESP, the green one, or EBP?
The green one is EBP
EBP. And how come we started it right there?
because I made a copy of ESP.
Oh, so you just put it where ESP would go since it's a copy of it?
Well, they point to the same place.
Oh, yeah.
Not anymore though, because the stack pointer keeps moving, right? Every time you push, the stack pointer keeps moving. So at this point, the stack pointer is pointing to the very last thing that I push. What about the frame pointer? It doesn't change because it is not affected by the push or the pops. So this is really nice because what this means is from here on, I can push and pop all I want, but EBP stays put.
So could
It
you
points
at the
to.
very end copy EBP into ESP and just like undo all the push and pop that you just did?
Well, it's not to undo. It ignores all the additional push and all the additional pops.
This is a good way to track parameters.
Exactly. Yep. So you're making all the connections. Why we are doing this. Yes.
Why do you care where the frame pointer used to be? Why do you care where the frame pointer used to be?
Because the frame pointer also belongs to the caller of this subroutine. The caller of this subroutine is probably using the frame pointer for exactly the same purpose. So if you don't save and restore the frame pointer, by the time you get back to the caller is going to misunderstand and think that its own frame pointer started here, which is incorrect. So it is always a good idea to say that, well, maybe this register is being used by my caller for something. So before I do something to destroy it, let me save it first, and when you're about to return, then you restore the content. So from the perspective of the caller of this subroutine, it is as if the register has never changed.
So is that call put car char? Is that the last command that used the frame pointer? Line 3.
Line 3.
Is that the one is that the last command that used the frame pointer? Is that what you're saving it for?
No. We don't know how the caller actually used the frame pointer.
Okay.
But whatever the caller used the frame pointer for, I have to preserve the value of the frame pointer from the perspective of the caller. So before I make changes to it, I should save it, and then right before I return, I will have to restore that. In other words, the modification to this program is not quite done yet. Okay, I still have one more instruction at the end here, well, two more to fix up this program. Okay. So we're now on to line 8. Line 8, these are fairly boring stuff, because we're just pushing additional registers. So I'll just go ahead and do this as quickly as I possibly can. I should write macros in a spreadsheet to do all this stuff. But I've never done it like this, for my assembly programming class. So this is the first time I use this particular technique to explain what happens on the stack. Okay, so we have EBX, and then we have ECX over here. Load ECX, and do exactly the same thing. Now, as I'm doing this part that is really boring, what you really need to do is to understand, how the stack pointer keeps moving, but the frame pointer stays put. Now, what is important to this subroutine? The parameter, right? The parameter is the important part that we have to get back to, and does the reference or does the relative distance between the stack pointer changes as we push and pop? It does, right?
Why is so special for a register so that we have to use it as a...
Okay, the EBP is kind of like the stack pointer. Now the stack pointer is special because the instructions push and pop, will automatically use ESP for the stack pointer. It does not use, EAX or any of the other registers. there's another instruction or another set of instructions that will also automatically update EBP as you use the enter and the exit, or the, I think it's called enter and leave. Those are the instructions. It will do exactly the same thing, but since I want to teach this class from the perspective of risk, so I'm actually doing everything with simpler instructions. But that's a good question. Yep.
Can you redefine what the frame pointer is pointing to at this point?
The frame pointer is still here.
Right, but what's it pointing to?
It's pointing to old EBP. That's what it's pointing to. Yeah.
It's not EAX.
Huh?
No, it's not.
Yeah, because lower addresses goes this way. So when your frame pointer is pointing to this location, it's actually pointing to the first byte of your old EBP.
So it points to the one behind it.
It points to the one. It points to this guy here. This is what it's pointing to.
That one. So okay.
Okay.
So
All right, let's keep going. Keep going. Okay, this is line 9, and then we have line 10 here. And this is the last one. Okay. This is the very last one. And
yeah, I was about to just paste the format.
does it do that?
From the previous file, it's here.
Okay.
Just shift it over.
Okay, so this part here is old EDX. Now this part actually is not important to our discussion, because what I want to do is to say, okay, we are done with line 10 in the instruction now. Line 11 is not doing anything that is particularly interesting to me. So I'll just go ahead and execute line 11 and line 12 without actually any references. Yep.
What happened to ESP again? Did EBP copy to ESP?
Say it again.
What happened to ESP?
ESP is the source of the copy operation, so nothing happens after the move L instruction.
So that's why it's not up there?
What?
So is that
The black bar is still ESP. The black bar is ESP. It just doesn't change, for that one single instruction on line 6.
So EBP is copied into ESP? Also, is that what it...
No, ESP is copied into EBP.
Oh, yeah, okay, I had it reversed, sorry.
Well, it is kind of important to study the instructions to make sure that you know which one is the source operand and which one is the destination operand. This is the stuff that we talked about in, I think, week 3. So it's very important that we know that stuff already at this
So
point.
EBP is like a bookmark to the beginning.
Exactly. It is a bookmark.
Okay.
Exactly. That's exactly its purpose.
You should update the ESP row with the L1 minus whatever's.
L1. Oh, okay. You mean this part here?
Yeah, you should.
Yeah. L1 minus 14.
Would that be a 1 minus 10?
Oh, this one doesn't change. That's
Yeah,
right.
that one doesn't change ESP.
Yep. L1 minus 14. L1 minus 18. This is like chewing wax. L1 minus 26. There we go. Okay, we're all good. Okay, yes?
So what happened to the line 11?
What happens to what? Line 11? Line 11 is not interesting. It doesn't do anything to the stack. Doesn't do anything to the stack pointer. Doesn't change anything to point somewhere else in the stack. And it does not change the content of the stack. I'm not tracking it.
So what you have in the code?
Because I want to print something. This is system surface number 4. Guys, come on. Come on. I mean, this is what we talked about on Tuesday, like 48 hours ago. Yep.
So, reason why you're saving stack pointer there into EBP.
Yep.
It's basically, like she's saying, it's just like a reference point.
Exactly.
You just want to restore back to the state you were in before the function was called.
It's not for restoring, it's for the easy calculation of stuff. Okay? Okay, now, we are now looking at line 13. Now, remember what line 13 and line 14 did before? The calculations are now off. They are not correct anymore. Because I pushed one more thing on the stack. So the distance between ESP and the first byte of the parameter is now off. Okay? But that's why I don't want to use stack pointer, because the stack pointer floats. Every time I push, it changes, the the reference or changes the distance from the stack pointer to the parameter, every time I pop, it does the same thing. So in order to know at any particular point of this subroutine what is the distance between the stack pointer and the parameter, I have to go through the entire code just to find out what is happening to the stack, which is inconvenient. But now I have a better way to do it, because the green bar has never changed. So if I want to do my calculations this time, I would just look at the green bar and say, hey, how many bytes are between this green bar, and also the bar that is the address of the letter J? It's just 8, right? So if I want to do this calculation, do you guys know how to adjust the instructions to do the calculation?
Would it be minus 8?
Hmm?
Would it be minus 8?
It'll be minus 8. It is 8 bytes before where EBP points to. Okay? So the time right now is about 7:52. If you watch the video again, this is the part that you want to watch again to do the homework.
What's the time offset from the start of the video?
Hmm?
What's the time offset from the start of the video?
I'm usually pretty accurate, so it can be off by maybe up to 30 seconds or so, something like that. So this would be the timestamp that you want, okay? 7:52 or so in the videotape, in the video recording. Yes?
So that means you just changed the code then, right?
Yes, you change the code over here. Instead of using ESP, you change it to the bookmark register, okay?
So
Instead of...
change it in the file so you can see it? Or?
No. This is part of your homework. You can do it. You can do it because you understand the general approach already. So what you do, I would just talk about it, and I'll let you guys figure out exactly how to do it. Yes?
You said the J is 8 bytes below, isn't it 8 bytes above?
No, it is below because lower addresses goes this way. When you go to the right-hand side, that's lower address, and that's EBP. Oh, you're right. It is plus 8. Sorry, you're right. You're right, and you're wrong.
I had the number right. That's all that matters.
It is. Exactly. So you're right.
Thank you.
That's all right. Well, the other thing you can also do is to see, when we took a snapshot of the stack pointer, the stack pointer was at L1 minus 10.
And we wanted L1 minus 2.
And we want L1 minus 2. So when the EBP is exactly at L1 minus 10, then you know what to do in order to get back to L1 minus 2.
So you want to update your timestamp?
Hmm?
You want to update your timestamp?
No, you guys can watch it. You guys can keep watching it. Okay, so this instruction has to be changed because we don't want to use ESP anymore. So change this to another register that we have talked about here, the green bar register. Okay, the green bar register. Yes, it is a technical term, the green bar register. And then on line 14, you also want to change this because the distance between the green bar register and the parameter is no longer 20 bytes away. It is, according to this, 8 bytes away. So you just change these two, then you are making use of the frame pointer now. You're no longer making use of the stack pointer anymore.
So it's our little frame of the stack.
The frame of your stack actually starts from the first parameter and it ends with the last local variable, which we don't have here. So in this case, your frame is just the parameter. Well, actually, it also includes OEBP. That's technically the end of this frame in this case. Okay, the rest of the program does not need to be changed, except when we get to the return here. Okay, now what's happening with these pop instructions? The pop instructions will basically restore the registers. Okay, so instead of tracking every single line individually, I would just combine line 17 to line 20 into one single instruction. Okay, because they are just 4 pop instructions. So together they will basically just get rid of or restore the values of EDX, ECX, EBX, and EAX. In other words, when at the end of line 20, our stack pointer will now be back to here. Actually, I should say all the way up to here. It'll be back to here. So let me change that. Question?
Yeah, do those 4s represent each register that you have?
Yes.
Because I know there's 5 of them, but there's 4 registers.
One column is 1 byte, and that's why there are 4 columns. Okay, so at this point, can I return?
No.
What happens when I return here? I'm going to use the address or the content or the value of old EBP as if it is a return address. When you do that, sometimes you may return to a valid place that will actually execute some code. Most of the time, it won't. Okay? But it's the wrong place to return, because what do we want to return to? We want to use the return address to return, right? And this is the wrong time. So what do I need at this point to get back there?
You need a pop.
Okay, we need to do a pop. Okay, very good. So let's go ahead and insert a new instruction here. And we need a pop what?
EBP.
Pop EBP. That's the whole idea. That's why we saved it to begin with. Because we want to restore the original value of EBP before we return to the caller, so that from the caller's perspective, EBP has never changed.
Pops are like parentheses. You never want them unmatched.
Sort of. You can actually sometimes, if you know that you don't need that content back, you can adjust the stack pointer and just basically free up the space on the stack without restoring it to anything. So you're partially right.
Excuse me? Can
Yep.
you say it again about the pop EBP?
Pop EBP, because we pushed it. If we don't use a pop EBP and just return at this point, then we'll use the wrong content on the stack to return. It is not our return address. The stack pointer is still here, right? So that means if I did not insert this instruction here, then we'll be using the value of old EBP to return to, and that's.
So you mean that you get rid of the green bar, instead we want to use the black bar, right?
We want to use the black mark is always telling you where the stack pointer is pointing to, but the stack pointer is not yet pointing to the right place for me to execute the return statement. This is where I put old EBP. That's why I need to restore old EBP first. Then oops, I put it in the wrong place, didn't I?
No, that's right.
That was it right?
Yeah, that's right, yeah.
Oh, that's right. Okay, because this instruction, the new instruction, which I will call line 20.5. There you go, line 20.5. Okay, so on line 20.5, we will execute the pop EBP instruction. So this will move over to here, so that when we execute a return statement, the return will actually use the correct content on the stack. And now everything is good. Yep.
Are you using EBP as a holding variable, or can you replace it with just any register, any variable to go? Or is it
Technically speaking, yes. But since there's a hardware instruction to do exactly that part, if you want to be consistent with the use of EBP, you should use EBP. The other thing that's okay, let me answer your question first, and then I'll go back to that. Yep.
Wouldn't it make sense at some point for our purposes to add 8 to EBP before we start using it, so that it's pointing to our arguments?
Yes,
instead of
but not in this case. In this case, the stack pointer is already adjusted correctly at that point. So we don't need to do any type of adjustments, at this point. But you are correct, in general. Okay, so let me just add one more instruction to basically say in general what you want to do. In general, assuming the stack can be unbalanced, in other words, you would have pushed stuff that you have not popped yet, okay? Because in general, that can be true. Then what you want to do, which in this case is not something that has any effect, is to put this instruction first before you pop EBP. So I'll call this 20.2. Okay, 20.2 doesn't do anything in this case because they are already exactly the same before the instruction on line 20.2. Yep.
I thought you couldn't change ESP. You didn't have any control over that.
Yes, you do. It's EIP that you don't have control over. It is the instruction pointer. So are we doing okay so far with this code here? Yes.
So line 20.2 doesn't do anything at all?
It does not do anything because they are already at the same place. Because if I had line 20.2, it would be here. And you can see that on at line 20.2, the black bar is exactly where the green bar is. So whether you copy or not doesn't really change anything. Yep.
What I actually meant was, for the purposes of using EBP to point to our parameters, wouldn't it be better at line 6.5?
No, you don't want it to point to your parameters. You want it to point to its own old value. Because, guess what? This is what a C compiler does. Now, why do we want to care what a compiler does? I mean, this just looks kind of overly restrictive. We are assembly programmers. We are all free thinkers. Maybe not. And so we want to be able to do things that we think is best when we program in assembly. So why do we have to do this? Why?
Consistency.
Well, it's consistency. But has anyone? Okay, go ahead. I just have to push my idea on the stack first so I can pop it later.
I
Go
think
ahead.
it's because the people who write the compilers have been doing this for decades. They've found that there is a good reason, and we should trust that they have one.
Well,
Never trust tech.
exactly.
You didn't write C compilers.
No, I did not. Okay, there's a reason why we want to basically respect all these rules that are used by compilers. Has anyone used GDB or any type of debugger to debug a C program? I'm hoping that at least I see a few hands. No? You guys all use C out to debug your programs? I am concerned. I am concerned. Okay, but when you use a debugger to debug a C program, you can actually find out how you got to where you are at this point. In other words, you can look at the frame, the call stack, so to speak, and it can tell you exactly how you got from main to subroutine 1, to subroutine 2, to subroutine 3, to subroutine 4, to subroutine 5, which is where you are. And not only that, it can even tell you the parameters that are passed on at each level of subroutine calls. Now, how can it do it? It's all because of this. It's because the relative position of the frame pointer, let me just get rid of the square here so we can show the green bar. The relative position between the green bar and the old EBP and the return address and also the parameters, that does not change. So now the compiler can use old EBP to go up one level of the call frame to the caller's own call frame. Then you can retrieve yet another one because it's just a linked list. It keeps going back. It can also locate the return address. Once you locate the return address, you know which function is responsible to push that part on the stack. And you can also, just use the green bar and retrieve all the parameters related to this function call because you know where to find the parameters relative to the green bar. Okay, so that's why we have to play by the rules, because when you play by the rules, then the debugger has actually a lot of information to help you debug a program, because you don't just stop at a certain place. You know exactly how you got to that place. Yes.
So what do we end up at the very end and back at the return address?
Now we're back to the return address, so we are ready to return. So just to make sure that we clean up this entire thing, so we are now ready to execute line 21. Line 21 is going to execute a return statement, so the stack pointer will be adjusted yet one more time. But the frame pointer is going to be adjusted after this. In other words, after we pop EBP, the green bar is no longer pointing here, because we restore it back to whatever value that you had, and I have no idea where it's supposed to point at this point. But that's the whole point, because it is just restored to whatever the caller had it, and that's all I care.
So you can't move it anywhere, you just have to leave it there because you don't know where you don't.
There's no way for me to say that it is no longer pointing here, the green bar. Okay, so now on line 20, we execute the return statement. The return statement will make use of the return address here. And all we'll do is to change the stack pointer so that it's pointing back to this point. And on line 22, we clean up the stack by adding 2 to the stack pointer. And it is back to where it was originally.
One down.
Oh, okay. Cells. Ding, ding, ding. Okay, there we go. So now we have the same, almost the same code, except it is now modified to be ready to utilize the frame pointer. And I will also be very kind and just highlight the 2 lines that you have to change for your program. Let me see how I should highlight it.
Is there a highlight button? Yeah.
Well, that's a background. I can.
Black. Oh, okay.
It's smart.
It is smart, yes.
It shops S-Mart.
Okay, so are we doing okay so far? Well, do you guys understand the basic concepts? You know, the idea is the concept. The math it will follow once you understand the concept. Yes.
Let's say if you had sub long to which way would you go then, to the right?
What?
Let's say the last statement was sub L $2 ESP. Would you move the pointer to the
Okay,
right?
wait, say again. What do you want to
Let's
do?
say line 22 was
Yes.
sub long $2. Would you move the pointer to the right instead of the left?
Well, you tell me. Lower addresses goes to the right.
There we go. Okay.
Yeah.
Because I think adding would when I think add, I think you want to move forward to the right.
Lower addresses goes to the right. When you decrease it, it goes to the right. When you increase it, it goes to the left.
That's so confusing.
That brought you
It is confusing, but that's the way it is.
That brought you back to what did that bring you back to?
What?
When you did the last add to.
Then we're back to the beginning,
Okay.
which is good, which is what we want. That's what we want. Yes. Okay. Okay. So now So I think you guys want me to save this file, right?
Yes.
Okay. It is now saved, and it is time to talk about just basic conventions. Okay, not really important stuff, just kind of basic conventions. So what I'll do is I will just give you a sample file here. Okay. And at this point, we haven't talked about how to return a value, so I won't use any function that returns a value. So now we have, I'll just call this function g, okay, so we don't confuse it with function f, because somebody's going to copy and paste the code if I may name it f. Okay. Somebody's going to do it. Okay, so we want to, so we'll, in function g here, what I'll do is I'll say, we have int, x, int y, and int z here. And inside the subroutine, I'll just say do something with x, y, and z. Okay, so this is the subroutine that I want to write in assembly. The first question is, how do you want to keep track of the distance between EBP and x, y, and z? We know that they do not change as you push and pop stuff, on the stack. But how do you represent it? So this is what I do. What I'll do is I would use the symbol definitions, and the first thing I do is OEBP gets to 0. Because what I mean here is EBP, the distance between what EBP points to and the saved EBP is 0. It is pointing to its own old value. Once you have the stack all set up, this is what happens. Okay. What about, what is the next thing? What is at 4 bytes above old EBP? That's the return address. So this is what I'll do. The return address is old EBP plus 4. Okay? So once again, the distance between what EBP points to and the return address is 4. Okay. What is on top of that?
Or data.
The parameters, but which one?
C, the last one.
Well, there's a reason why we push parameters backwards. The last one that you push has the lowest address. So which one do we push last? X. X is the one that we push last. So that means x, or the displacement to parameter x, is return address plus 4. The plus 4 has to do with the size of return address itself. Okay?
So...
That's not what I want. There we go. Yes?
So x would be located at or 0 open parentheses, comma.
You can use the base address input, yes.
Okay, you can.
So now we can say this and that, right? Yep.
So at the line x equal return address plus 4, you mean you pop it?
No. This is just defining the symbols. I'm just trying to calculate the distance in terms of byte locations from where EBP points to, once it's set up correctly, to the several objects that I have on the stack already. I'm just calculating, where are these things relative to where EBP points to the green bar register.
Okay.
Yep.
Shouldn't there be a -4 if it's going
No.
down as you're adding to it?
No, it's +4 because the frame pointer is down here already. EBP +4 is the return address. EBP +8 is the first parameter. It is correct because when we push, you're changing the address to be lower. You're changing ESP to be lower. And we don't take a snapshot of EBP until we are in the subroutine itself. So at that time, we also do this after we perform the push EBP instruction, and that's why these calculations are actually correct. The other side of EBP actually has special meanings too, but we are not there yet. We have not talked about local variables. That's where local variables are located, is on the other side of where EBP points to. Okay, so now we can just define the subroutine. The subroutine is label G. Now, in this case, you also have to do a dot. Yep. You also have to do a dot global G, because dot global G to the assembler means, oh, I think somebody else might need to know, how label G is defined so that the linker can actually figure it out and say, oh, okay, somebody else is trying to call function G, and this is where function G is.
So
Yep. Nope.
So it's like the pointer to a function?
No, G is the name of the function. G is the name of the function. So inside G, the first thing you want to do is to push EBP, because remember, we want to save the register before we change it. And the second thing we want to do is to take a snapshot of the stack pointer so that we set up our frame pointer. Is that good so far? And then we have the ... here to do something about it. At the very end, we will use exactly the opposite instructions. Whatever is we move in the opposite direction. Whatever we push, we pop, and then we have a single return at the very end. Okay, is that okay so far? Yep. The ... No, but this is. If I want to change this C function to do something that is absolutely stupid and dangerous, like that, then how do I do it?
Push.
It's easy, right? What do I push first? What is the last parameter? Because we push the last parameter first. Z. Can I do it with one single instruction?
Push LZ.
Push L, Z. That's not going to work.
Z open parentheses %.
Because what is Z? Z is basically, an alias of what, 12, right? Because this is 8, 12, this is 16. So Z is basically the number 16. I just do the calculations relative like this, so that if I change the size of one parameter, I don't have to change everything else. Yep.
Well, if we were to take this code and compile it right now, that would have worked, right?
Yes. It would have.
Oh, it will?
Yeah.
So you're defining X, Y, and Z to be proper labels?
Yeah. They're proper. I mean, all a label is really just a symbolic name that has a definition that is a number somewhere. And this is fine. Okay? So, and then we have to push Y using the based addressing mode, and then push X using the based addressing mode. And then we perform the call to G. And then when we are all done here, we have to adjust the stack pointer by 12 because we want to free up those 12 bytes. Well, trust me, we don't have to worry about this part here because it will never come back. Right? Because this is a recursive call and there's no condition to stop it, so it would just keep going like that and you'll run out of stack space at some point. But the whole point is to illustrate how to compute the distance between EBP and parameters, and two, how do we access the parameters inside the subroutine? This is why we have the based addressing mode. Okay. Now, does everybody see why this, why z open paren EBP close paren is going to get the value of the register? Excuse me, the value of the parameter z.
Yes.
Because this is a memory operand. A based operand is a memory operand. It goes to memory to get something. But what is the effective address of a based operand? It is the base register, which in this case is EBP, plus the constant that is outside of the parentheses. In this case, z, by its very definition, is the distance between where EBP points to and the parameter z itself. So we are actually going to the address of the parameter, grab those 4 bytes, push it on the stack to set up for the next call frame, do the same thing with y, do the same thing with x. Now we have all 3 parameters pushed on the stack. We perform the call. When it comes back, if it does come back, then we will add 12 to ESP because we used up 12 bytes on the stack for the parameters. Now it is time to free up those 12 bytes. Okay. Are there any questions about this code here? Yes?
Okay, so I'm just trying to relate that to the spreadsheet that we just did. In the other spreadsheet, it went J, then return address, then old EBP.
Now that is a little bit different because in that example, we have to compute the address of the letter J that we push on the stack. In this case, we are not computing the address of Z, Y, or X. We're getting the content of those parameters.
But I'm just saying, okay, so maybe it's not exactly about that, but just in the way it's viewed on the stack.
Mm-hmm.
It was J, then return address, then
Correct.
old EBP. So there it would be Z, Y, X, return address.
Yes,
EBP.
yes, because Z is the one that has the highest address, which means it is all the way to the left-hand side from your perspective. Okay. So are we doing okay so far with these concepts? The math, you can worry about that later because once you understand the concept, the math will just come. But this is a good illustration. I really think this is a good illustration because it illustrates the perspective from the called subroutine perspective. It also look at things from the caller's perspective because G calls itself. This is the caller's perspective. That's the callee's perspective.
This file is going to be available after class?
Yes. The spreadsheet, the video, this program, everything. Yep.
Can you compile link breakpoint on G and run this for us? Can you compile link
Yes.
breakpoint on G and then run this for us, please?
Absolutely. You want to put where do you want to put the breakpoint again?
On G.
On G?
Yeah.
Oh, okay. Well, G is already a label. I don't need a breakpoint.
Well, G itself is a label, but you can use the breakpoint set.
Well, I just need to finish the program, and since I'm running out of time, I won't combine, I won't use 2 different, source code. I'll just do it like this. So in this case, I'll just call G. I don't really need this part here because, it will never exit. It will never come back to this point. But we'll just pretend that it does. Okay, so now we have AS G steps.
When you have defined the G label, why you need the dot global G?
When I define the label G,
Yes.
What
Why
about-
do you need the dot global G above of the
Up
label
even
G?
In this case, he's asking about the global G for the linker at the top. In this case, you don't need it, but
Oh,
in
okay.
practice.
I forgot to do one thing because I forgot to pass the original parameters. This is the nice thing about doing it in assembly because if you forget to pass parameters, it won't complain. Okay, we'll just pass 3 as Z, 2 as Y, and 1 as X, so that we can actually test to see those things. Add L12 to ESP, which is pointless, but we'll do it. LD, GDB, sample. Okay, put a breakpoint on G, BG, and BG. Yeah, cool. Okay, so we'll run the program, and now we are at the. It's at the wrong place, isn't it?
No, that's right.
No, we need to push EBP first.
Yeah, it's supposed to have the push EBP over here. It didn't stop at the right place.
Maybe
No,
GDB
It
thought
pushed
it was
at
just
the-
a normal
it
C
stopped at the
program or
G,
something.
The call G. I believe, no.
No,
Well, it stopped on line 20, that's the line 20.
I think we need a no op, because that's the first part of the program. Okay. No, still wrong.
Just let it run.
Put the first one at line 17. Run again. And this time it does stop at the right place. So I think there's a global variable G of some kind somewhere that is at the wrong place. I don't know. Okay, so right here we are stopping at the very first instruction of the subroutine. So one thing you can do is to display the content on the stack at this point using for x slash whatever number you want to display, and you want to display in hexadecimal most of the time. And this is where starting with where the stack pointer points to. And this looks right at this point. This is my return address. This is parameter x, parameter y, and parameter z. So everything is in the right order, and it's all cool. Okay, so the next instruction is the no op instruction, and then the push EBP instruction. After the push EBP instruction, there will be 5 items on the stack, like this. Basically, old EBP turns out to be 0, okay? Because we are underscore start is the entry point of the entire program, so there was no subroutine before underscore start, and that's why old EBP is just some value that may not correspond to any place on the stack, which is fine. We'll just restore it back to 0. And then we are now going to execute move ESP to EBP. So now we have to take a look at ESP and EBP, and sure enough, they are exactly the same because the move instruction is just making a copy of those two. And then now we are ready to push the 3 parameters. So I'll single step the 3 pushes here, and we are calling again. Okay? So calling again, now we're inside the subroutine again because of recursion. It is a good time to take a look at the content on the stack again. And we'll take a look at the 4 items. And you can see that I constructed the parameters on the stack exactly the same way that they were, because that's what the recursion does. The recursion, is just pushing x as x, pushing y as y, and pushing z as z. Yes?
Can we view a few more variables on this here stack?
Yes, you can. No, you cannot. Okay, if I display 8 items, this is what we see on the stack. This is the current call frame. The current call, well, we are not done with the frame yet. This is the return address, parameter x, parameter y, parameter z. This is old EBP of the previous invocation, and this is the return address of the previous invocation. This is parameter x of the previous invocation, parameter y of the previous invocation.
So if you were to single step and go back, we'd actually get the F52Z, 52C on top of that 0804.
Sorry?
When we push the EVP again, we're going to get that
Yes.
address up there.
Let's
Well,
just
go ahead
continue
and-
through this one.
Let's go through the push EBP, and we'll see what happens on the stack. And this time I can display even more items, just so that we can see what's on the stack. This is the old EBP of the current invocation, and this is the old EBP of the previous invocation. Okay. So this is a good program to look at and actually to borrow ideas from, because this is how I would write a program, that is written in C and translated into assembly, is to do it like this. Okay. Are we doing okay so far? Do we have enough to start with the homework assignment?
We have enough to finish the homework assignment.
By tomorrow,
We have enough to finish the homework assignment.
Sorry?
Like
Multiple files?
Like having to assembly and function in different files. I want to see it.
You want to see the mixing of
Yeah, multiple files.
multiple files? It's already done.
So,
Hey Kat, how many F's are in your test cases?
What?
F, the letter F. How many of them are in your test cases?
The letter F?
Yes, for the last one. The value